Bismillahirrahmanirrahim. Welcome to the new lecture of data communication and networking. Today we are going to be study about the analog to digital conversion. So it is the second part of chapter 4, and the chapter 4 was about digital transmission. So analog to digital conversion. So why we convert analog to digital? So a digital signal is superior is an analog signal because it is more robust to noise and can easily be recovered, corrected and amplified. For this reason, the tendency today is to change an analog signal to digital data. In this section we describe two techniques: pulse code modulation and delta modulation. But today we will be just study about the pulse code modulation. So in a pulse code modulation we have three concepts. The first concept about sampling. What is sampling? Just keep in mind, sampling is like a frequency. If you have a frequency of a 2 hertz, so just convert 2 hertz into sampling rate of a 2 sample per second. Simply, if you have a 4 hertz, so convert 4 hertz to 4 sample per second, and so on. The second is quantization. What is quantization? Quantization mean if you have a let's see, if you have a value of 1.2, 1.3, 1.4 or 0.1, 0.2 and so on. If once we have a value in a fraction, so in a quantization what we can do, we can round off this value to the some other value. Like 1.2, we can say 1 point is near to 1.5, so the round off value will be 1.5. If you can see that we have a value of 1.9, it's a fraction value, we need to be round off, we can say it equal to 2. So this is called quantization. Okay, and the third is binary encoding. Binary encoding means so how many bits we need to be encode with the digital signal once we convert analog to digital. So before we sample, we have to filter the signal to limit the maximum frequency of the signal. It affect the sampling rate. So just about talking about the frequency, so you need to be limit your frequency. So later on you will see how it can, but just keep in mind that the maximum frequency need to be a limited one. And the filtering should ensure that we don't distorted the signal. For example, remove high frequency common that affect the signal shape. So basically why we say about this, because we have a three different kind of a filter. We have a low pass filter, band pass filter and high pass filters. First let's see, this is, I'm showing you three different filter now. Okay, so let's see, it's our low pass. Low pass always start from 0 to up to some value, I told you before. Band pass start from midpoint to the some mid value, and the high pass start from any of your value, and then it will be and so on. This is like infinite. This is a high pass filter. So mostly we are using a band pass filter because we have a limit of frequency. And one thing more, hope you guys know about a jammer. In a jammer we always use like the band pass filter. So this is low pass, this is band pass, this is high pass filter. That's why we need to be limit our frequency. So coming to the PCM block diagram. In PCM block diagram we have an analog signal first of all, so we need to convert this analog to the digital signal. So once we are converting analog to a digital, so first we need to do a sampling. I told you sampling is just like about frequency. You have this signal, just make a sample. This is sample 1, let's see, this is sample 2, let's see, this is sample 3, like this way we make a sample. So first what we can do, we can do a sampling. Then with the sampling we just add a PAM signal, pulse amplitude modulation signal, which can show the sampling. Okay, then after that we can do a quantization. Quantization means once we have a value of amplitude, this is the value of amplitude, let's see. Okay, this is value amplitude, and this amplitude is equal to 1.2, 1.3. So in a quantization what we will do, we will round off the number, like 1.2 is equal to 1.5, 1.9 is equal to 2, 2.3 is equal to 2.5. so like this we just round off the figure. That's called quantization. After the quantization, what we can do, encoding. What kind of encoding? Binary encoding. So this is basically a block diagram of a pulse code modulation, which is used for the converting of analog to digital signal. So coming to the sampling, so what is sampling? Sampling signal is sampled every TS second. TS means sampling interval. So T is your sampling interval. Your sampling frequency is always equal to 1 over TS is called a sampling rate or a sampling frequency. There are 3 sampling method now. So we have a 3 sampling method: ideal, natural, and Fletchoff. So in these 3 we have a different block diagram. So in ideal we can say that an impulse at each sampling instant. So this is your ideal. At each instant, at each point we have an impulse. Impulse means just like a spike. Okay, this kind of spike is called impulse. The second is natural, a pulse of a short width with a varying amplitude. So a short width, if you can see, the width is going to be short and amplitude is going to be changed, is varying. The third is Fletchoff. So sample and a whole, like a natural but with a single amplitude value. So this is your Fletchoff. It's just like a block. Okay, so this is we have these 3 different sampling methods. So according to Nyquist theorem, if you can remember it, so Nyquist said that the sampling rate must be at least 2 times the highest frequency contained in a signal, if you remember that. So this is about Nyquist. So our sampling frequency will always be greater or equal to the 2 of highest frequency. Okay, so now you can see the Nyquist sampling rate for low pass or a band pass. So you know about the low pass now. This is your low pass signals, and the same frequency and the same Nyquist rate or the same sampling rate will be applied, 2 of its maximum. Okay, this is your band pass, and in the band pass again the same concept will be applied of a Nyquist. Okay, same formula, but the band pass, you know about the band will start from the mid to the highest value. So coming to another figure, just like for your information, recovery of sampled sine wave for a different sampling rate. So this is your sine wave, which is the sine wave is the same, but the sampling rate is going to be changed. So if you can see, this is your Nyquist, which is equal to Fs is equal to 2f. Okay, this is equal to Ffs is equal to 4f. How it's going to be changed? It's going to be changed about the sampling rate. We can say here is 2 sample, here is 4, it is just 1. So the sampling rate is going to be changed. 1, 2, 3, 4, 1, like a sample. So the sampling rate is going to be changed. So one thing keep in mind. So in a 1 second, like we see, this is your 1 hertz. Okay, up to this is your 1 cycle, and I can say this can be 1 sampling rate, and we can say it can be 2. We can make it 4 as well. So how many samples we can make? We can say like division 1, 2, 3, 4, 5, 4 samples. Okay, well, that's just for your information. Later on we will see how can it work. So coming to the quantization, so the sampling result is in a series of pulses of varying amplitude values ranging between 2 limit, minimum and maximum. So in the quantization we just assign a maximum range for amplitude and minimum, and it will be your mid one which start from 0. So maximum and minimum. So that's called quantization, and we will be round off the sample with according to the maximum and minimum value. So the amplitude value are infinite between the 2 limit. We need to map the infinite amplitude value onto a finite set of unknown value. So this is achieved by dividing a distance between minimum and maximum into L zone, and each of the height will be delta. So this is called maximum minus minimum divided by number of level. This is the formula. So quantization level, the midpoint of each zone is assigned a value from 0 to L minus 1, resulting in L values. Each sample falling in a zone is then approximately to the value of a midpoint. One thing keep in mind, just telling about it, basically we will apply all these things in a practical view, an example, and so once you are going to be solve the example, so you will understand why we are talking about these factors. Okay, so coming to the quantization zone, assume we have a voltage signal. Let's see, we are assuming supposition is about the voltage level X. V minimum is equal to minus 40 and maximum is 40. Okay, so we want to use number of a level which is 8. 8 means 2 raised to power 3 bit per level. Okay, so 20 minus 20 can be 40. 40 divided by 10, 5. So width zone is 5. So the width zone, I'm telling you, with the width zone mean the difference between the amplitude zone. It can be like a difference of 5. Okay, it's like a difference of 5. We have a 8 level, so 8 level can make it by 5 difference. So 1 2 3 4 5 6 7 8. So it can be first, it can be 0 5 10 15 like a 40, then a 1 2 3 4 5 6 7 8. So this one is 0, so it's minus 5 minus 10 minus 15 minus 20, then plus 5 10 15 20. Okay, so this, so the difference of 5. Then number of level is 8 level, difference of 5. The 8 zone can be like this value, the midpoint, or so it can be midpoint 17.5 12.5 7.5 2.5 2.5 7.5 and so on. How it can just 8 17.5 plus 17.5, so you know what should be your final result. So this is kind of midpoints of the zone, so you can easily find the mid zone. Now you can see an example, it's very easy. So come assigning code to zone. So the formula which is used for number of bits is how many bits we can be using a level. So number of bits you log of 2 with the L, so we have 8 levels. From this formula you can get number of bit will be 3. Okay, so 3 bit is going to respond is 8, so your combination of a 3 bit will be 0 0 0 0 0 1 0 1 0, so it like 0 1 2 3 4 5 6 and 7. Okay, so you guys know about it. So now coming to the example, how we can sample, how we can quantize, and how can we select a number of a bits. Okay, now we can come to the our basic and important thing where we can apply all these things in a one example. Okay, now coming to the figure or example 4.2, say quantization and encoding of a sample signal. Okay, so let's see, this was your analog signal. This was your analog signal in this time, and you want to make, or you want to change into a digital signal by using a sample. So the first thing was like the sample. This was the sample 1, sample 2, we take it, sample 3 4 5 6 7 8 9 10. So this thing will be available in exam. So maybe the analog signal with the sample rate. Okay, so this is your analog signal, and we convert it to a digital by using a sample, and your sample are available here now. Okay, then what we can do, so we can make a zone width. So as you check this, whatever the zone width is 5. Okay, so start from 0 0 5 10 15 20. So this is just like a width zone multiply with number. Okay, so just we are using that 1 2 3 4 1 2 3 4 plus and minus. Okay, so 0 1 2 3 4 0 1 2 3 4. So this is your amplitude. This is your amplitude. Basically your the amplitude is minus 6.1 7.5, but which amplitude or which number we will use, I will tell you later on. Okay, so this was all your amplitude. This was all your amplitude values. So initially what we can do, the first, how many bits we have 3 bits. So how many level we have? 2 raised to power 3 is equal to 8. So we have 8 level, which start from 0 1 2 3 4 5 6 7. So how many level we have? 8 levels. 8 level we have. So initially we need to find normalize pulse amplitude modulation values. So now we are going to exchange this amplitude value with the value of level. Okay, so if you can see this value is compared with this one, it's come down. If you can see, okay, let's see this is your 1, this is your 1, so it will be 1 point something, so it like equal to 1.22. so this is your PAM value. PAM value is equal to 1.22. then come to this value, it can be 1.5, it can be 16.2, so it can be like a 3.24, it can be 3.9, it can be 2.2, it can be 1.1, it can be 2.2, like it can be 1.8, it can be 1.2. so these values called pulse amplitude modulation values, which is gets by from normalized amplitude value which we selected on this point. So this is your normalized amplitude value, and we can get it from this value. So 0, 1, 2, 3, 4. So using minus and plus value as well. Minus. So we all get all values from normalized one. So now coming to the quantization. So in a quantization, what we will do, we will make it to a round off figure, and our round off figure, if you remember the midpoint of it, the midpoint can be these values. So the 1.22, so we can get it by, we can say it can be equal to 1.5 normalized quantized value. So normalized amplitude, it can be normalized PM value first, then the second it can be normalized quantized value. But in a quantization, what we can do, we can round off. So 1.22 can be equal to 1.5, 1.5 always equal to 1.5, 3.24 equal to 3.5, 3.9 equal to 3.5. we cannot use a 4 here, because why? Later on I will tell you, if it could be 4, and so when we are going to convert into quantization code and encoded word, then we cannot find it. Okay, so that's why if our bit is like if our level was 16, so in such case we can use that, but in this case we cannot. We can use up to 3. So 3.5, 2.2 can be 2.5, 1.1 is equal to 1.5, 2.2, 2.5, 1.8 equal to 1.5, 1.2, so and so on. Okay, so now this is our quantized value. So 1.8, so we always use which values? Mid value. That's why we cannot use 1, 2, 3, 4. We can use the mid value, 1.5, 2.5, 3.5. Okay, so use the mid value for the normalized quantized values. Okay, got it? Same on this point, from this line, this vertical line. So now coming to the error between normalized PM values and normalized quantized value. Just subtract this value from this one, so your normalized error will be 0.38, 0 error plus, so this is your error. Okay, this is your PM, this is your quantized, this is your error. Now, so now the most important thing is quantization code. Which code we need to be select from the graph to the graph. So this was the comparison between normalized PM value, normalized quantized value, and the normalized error. So now coming to the quantization code. So if you can see this value in the front of the quantization code, so it can be equal to 2. Okay, so this quantization code is selected by number of a level, because we have 3 bit, 2 raised to power 3 is 8. So start from 0, 1, 2, 3, 4, 5, 6, 7. So this is your 8 level. So you can, it's up to you. All these values depend on your choice. Okay, let once we select number of values here, so you can select minus 20 by 15, 10. It's up to you. It's your choice of selection. So this value is equal to quantization code is 2, then this is equal to 5, this one is equal to 7, this is again 7, so and so on. So all this is called quantization code, which is collected from this quantization code. Okay, so the most important thing, the number of bits is we studied here, number of a bit. So how many bit we can select for a zone now? So 2. So 2 is your decimal number, convert into binary, which is equal to 0, 1, 0 bit. This is your number of a bit, but we are using 3 bit because we have a 3 bit, and 3 from 3 bit we select a 8 levels. Okay, convert 2 to binary 0 1 0, 5 to binary, 7 to binary, 7 so all is your binary number. So now the thing is, once you are sending your analog signal and convert it to digital signal, and your digital signal in a receiver side, you are receiving these bits, so this is basically analog to digital. You had a analog signal, and in the receiver you have a digital signal now in the form of bits. So quantization error, what is quantization error? When a signal is quantized, you introduce an error. The coded signal is an approximation of actual amplitude values. The difference between actual and a coded value is referred to as the quantization error. The more zone, the smaller be the weight, which result in a smaller error. So this was the basically the PCM coding, where we can convert analog to digital conversion. So coming to PCM decoder, we study about PCM encoder. Now we study about PCM decoder. The same concept, same thing, just but in a opposite view. To recover analog signal from a digitized signal, we follow the following step. We use a whole circuit that whole amplitude values of the pulse till the next pulse arrives. We pulse this signal through a low pass filter with a cutoff frequency that is equal to the highest frequency the pre-sample signal. The higher the value of L, the less distorted a signal recovered. The same concept just now you can see in this block diagram. The component PCM decoder. So now the digital signal is received to a receiver, and the receiver wants to decode the digital signal to analog signal. So what we can do, we have a make and connect the samples from here. Then the signal, the amplitude, we need to be have it coming to like add with the digital signal samples. After this we have a low pass filter. In a low pass we need a low frequencies, as I told you before. So in a low, once we collect a low frequency from this point, from this section, then we will have a analog signal again. So this is a basically review the PCM encoder and PCM decoder. Once somebody can ask you to find out, then draw the PCM encoder and decoder block diagram. So as you observed here, and somebody says, okay, convert analog signal to a digital signal, so you need to be use the PCM encoding stream. So now coming to the transmission mode. So in transmission, the transmission of binary data across a link can be accomplished in either parallel or serial. So we have two kind of a transmission mode, parallel and serial. In a parallel, we can send multiple bit with each clock. In a serial, we can send one bit by one. Okay. So in a block diagram, you will be understand it in a well. So the topic we will study here will be parallel transmission, will be serial transmission. So parallel transmission like this one, number of bit will be available at point. Serial transmission like this one by one will be bit will be available here. So the data transmission mode, like in a data transmission we have a two type, parallel and a serial. In serial we have a three, another asynchronous, synchronous, isosynchronous. Okay, so we have three different type in a serial transmission as well. So coming to the parallel, in a parallel just you have a number of bits, so we can send multiple bit at the same time. So number bit can be sent at the same time. We need 8 lines. So same concept, sender can send 8 bit, receiver will receive a 8 bits. Then in serial we are sending a bit by one. One will be received, then another bit received, another bit, and so on. Okay. So this is basically parallel serial converter. The 8 bit are sent one after another. We need only one line, and a serial parallel converter. So if you remember, if you see this one, we need a 8 line here for a parallel, but in a series we have need a 1 line. So in a serial we have a different type. In asynchronous transmission we send one start bit 0 at the beginning and 1 or the more stop bit 1 at the end of each byte, there may be a gap between each byte. So this is about just then the asynchronous here mean asynchronous at the byte level, but the bit are still synchronized, their duration are the same. So this is just like if you can see here. So the in asynchronous transmission, what will be our procedure? The procedure like the first bit will be the 0 and the last bit will be the 1. So the first bit will be a start bit and the last bit will be a stop bit, and the direction of line will be in this direction. So we have a number of a data now. So in number of data we need to be sent to a transmission using a asynchronous transmission. So the first bit will be 0 and the last bit will be 1. The first bit will be 0, the last bit will be 1. So this is the and the gap between the units now. So 1 and 0 will be have a gap, 1 and 0 will be have a gap. So the gap between data unit like this one. So the how we can differentiate the first bundle with the second, because in the first, like in this bundle, we have the last bit which is 1, in the second one we have a first bit which is 0. So this is the gap between, and this is the separation between the two bundles using a 1 and 0. So this is the method of a asynchronous transmission. In a synchronous transmission, we send bit one after another without start and stop bits or a gap. It is the responsibility of a receiver to group the bit. The bit are usually sent as a bytes, and many bytes are grouped in a frame. A frame is identified with the start and end byte. Okay, so this is like a simple one, like you can see here. Like a synchronous transmission, we just have a number of bits. No need to have a first and a start bit and stop bit. So we just have a simple frame. So this is the responsibility of a receiver to differentiate each and every bit and a bundle of a data. Okay, so this is about synchronization. When the clock of a sender and receiver are synchronized, so due to synchronization, so the receiver can be collect the actual and the power and the clear data from a sender side. So this is the last one, isochronous. And isochronous transmission, we cannot have uneven gap between a frame. So transmission of bit is fixed with equal gap. So this was your lecture. Hope you guys understand about analog to digital conversion and a parallel and serial bit transmission, which is so simple. That's why I didn't explain a lot. On a block diagram, we can easily get it the concept behind. So thank you for your time. See you in the next lecture. If you have any question regarding anything, so mention on a comment, so I will try to solve it and well share with you the answer. Thank you for your time.